Okay, so the title of our presentation is the Approximate Number System and the Treatment of Vagueness in Conceptual Spaces. And maybe let's start with a little history, because our presentation is actually based on our joint paper with Paula, which was published in a monograph, Cognition, Number and Meaning. And if you can see the exact reference to this text, so you can check it out and just email me if you find it attractive or something like this. So maybe let's start with the chief aim of our presentation. And the chief aim of our work with Paula was to actually formulate a conceptual space model which accounts for the conceptual structure of human processing and understanding of quantitative information. So in this particular talk, we will ask about content of the numbers related to one of the core number cognitive systems, namely the approximate number system. In short, it's ANS. So how do we get to our preliminary proposal? So firstly, we would like to present a paradigm in a number cognition, according to which humans actually are equipped in an innate pre-verbal system that allows them to process quantities without using the symbolic representation. And in particular, we will present the approximate number system, which is actually a quantity-specific cognitive system that allows humans to approximate cardinalities of discrete sets bigger than 4. Secondly, on the basis of this ANS presentation, we are going to observe that the model of these pre-verbal representations need to take into account vague borders between representation generated by the approximate number system. Thirdly, we will present a way of constructing the conceptual space proposed by Igor Duven and Liv de Kock, yes? Yeah. And other collaborators that actually allows taking into account non-determinacy of reference caused by vague borders between neighboring concepts. And finally, using this treatment of vagueness, actually in the last part of our talk, we will propose the conceptual space model of ANS-related representations. So, okay, so let's start with the observation that actually, according to a paradigm defended by many cognitive scientists, humans actually share with animals an abstract sense of quantity. And this sense is called number sense. And at the basis of the number sense and also the human numerical abilities actually lay two innate core cognitive systems responsible for pre-verbal representation of quantitative content. So these systems in some way actually also support interpretations of numerical expression when the symbolic concept of numbers created. So the first one, or maybe not first, but one of the systems is called the system of parallel individuation, and it actually allows us to identify in an exact way sets up to 4 elements. Maybe even not sets, but it actually allows us to track 4 elements at one time, because it doesn't provide us with a notion of set. And the another system is the system of of approximate numbers. And this system actually allows us to approximate the cardinality of sets bigger than 4 elements. So what is especially important for our study in the numerical expressions, that the numerical expressions gets its first conceptual content from these representations generated by this system. So this is absolutely fundamental thing for the number cognition, you may say, actually. So, okay, so let's start with the first system, the system of parallel individuation. And to illustrate how it actually works, we can use the story of Alice looking at the rabbit running to the rabbit hole. You probably know the story. So imagine that Alice is actually seeing a rabbit, and she's asking herself how, or maybe not was, the question actually is how this information is represented by Alice in terms of numbers or numerical cognition. So according to the paradigm explaining the number cognition that we base our investigation on, the parallel individuation systems actually enables Alice to create an individual item corresponding to the individual object that she is actually perceiving. So in other words, we may say that if she actually seeing one rabbit, the system will provide her a mental representation of one object. Okay, so this actually works only up to 4 elements. So if she's trying to identify the actual number of 4 rabbits, the system is able to represent 4 items in Alice's mind at one time, and it happened actually without counting the elements. However, 4 is said to be the upper bound of this parallel individuation. So if the number of elements is bigger than 4, Alice will not be able to identify the actual number of elements without counting them. This is due to the capacity of working memory, basically. So this is how it works. So it is important to note that the parallel individuation system is actually not strictly a quantity-specific system, since it is actually not directly intended to represent numbers. Instead, it's intended to create and sustain in working memories mental models consisting of up to 4 elements, such as things, for example, sounds, events, etc. So the parallel individuation system actually provides no common symbol for 2 or 3 elements, but offers 2 or 3 separate symbols for each respectively. So the representational structure of the systems looks like this, and what is here quite important, note that there's only one symbol for each individual. No matter it's image, abstract, or specific object, actually there's only one symbol for each individual, and there's no symbols for integers, and not even symbol of set, or not even a common symbol for all the individuals. So, second system responsible for this pre-verbal representations of quantitative content is approximate number system, and in short, we may say that this is also a cognitive system, but it actually provides directly a mental representation of the approximated quantity of elements in the set. So, if we go back to the story of Alice again, wondering how does she represents perceived rabbits, as I mentioned before, is the upper bound of parallel individuation system. So if the number of rabbits is actually greater than 4, Alice will be not able to identify the actual number of elements using the parallel individuation. So the question actually is, how does Alice represent bigger cardinalities? And when the number of items is bigger than 4, Alice will represent the number of rabbits or elements by a continuous magnitude representation of ANS, and it's also analog. So what is here important is that if the number of elements gets bigger, the representation also gets bigger. Like you can watch. So the size of this ANS representational structure is proportional to the number of perceived units, basically. So for this reason, ANS-related representations are often referred to as representations of analog magnitudes. And this analog characteristics of ANS means actually that all inputs provided by the systems are represented by continuous data. So this is how it works. So in other words, a mental representation of a set consisting of, for example, 12 elements will be twice bigger than a mental representation of set consisting of 10 elements. So the ANS-related representations work as an interconnected whole. This is another quite important feature of the system, and this means that the approximation of the cardinality of a given set is possible because it is put into correspondence with other representations in the system. And all estimation of size happen through comparison to the rest of the elements, and these comparisons of size actually of multiplied sets are based on the function of the ratio. So this is quite essential feature of the systems. So in other words, the distinction between 10 element set and a 20 element set is as difficult to make as a distinction of 20 and 40 element sets, since in both cases the ratio of the amount of elements is actually the same, and it's 1 to 2. Okay, so the actual behavior of this approximate number system is described by 2 effects. First one is called the size effect, and it occurs actually when the absolute difference between the 2 pairs of a set is constant. So then the sets with a smaller number of elements are easier to discriminate. And you can say that the straightforward consequence actually of this observation is that the difficulty of discriminating between 2 sets is not dependent on absolute difference between their cardinalities, so it's totally irrelevant. Okay, to illustrate this, how it actually works, I think that this is quite intuitive when we analyze a case in which the absolute difference between two pairs of sets is the same. So let us take two pairs of sets, one consisting of 14 and 8 elements, and the second one consisting of 66 and 60 elements. So as you may see, although the absolute difference between the amounts of the elements of the two sets is 6, so it's the same basically. It is much easier to distinguish between the first pair of a set than the second one. So this outcome is actually quite intuitive, and it was also proven experimentally, so basically we don't want to discuss with it. The second effect, which describes the behavior of ANS, is called the distance effect, and according to this effect, it is actually easier to discriminate sets that differ by a significantly larger number of elements. So to illustrate this, as you can see, it is much easier to notice the difference between 14 and 6, for example, elements in the set than between 14 and 13 elements in the set. Yeah? Okay. So another feature of INS that we are going to use in this talk is the fact that approximate number system gets activated not only by discrete sets of elements, but also by a symbolic input. What does it mean? Okay, so let me illustrate this with a simple story. So imagine that you're entering the bar and you're actually looking at the shelf behind the counter, and even without your conscious willingness to estimate the number of bottles standing there, your brain actually makes some reaction to approximate the numbers. So it approximates it in relation with experiences you might have had previously in your life, and hence it positions your estimation actually on the approximate number line. So it forms a line. And if you're actually sitting in the bar for too long time, you might actually start seeing the same number of, for example, rabbits, even though at this point you might be unsure if it's actually the same number of rabbits, but let's assume. And this will be actually the same representations that will be generated by the symbolic input 94. So in other words, the group of bottles, hallucinations of rabbits, and symbolic input 94 may actually cause the same representation in your minds. Okay? So how does it work? Well, consider the number line of exact numerals, okay? And thanks to the training in the counting routine, we knew more or less, at least, where at this line is position of the number 94. Okay, it is right here, yes? So this number actually represents the quantity of elements, in this particular case, quantity of numerals, preceding it in the number line, yeah? So, and the number of these preceding elements is exactly the same as the number of elements on the bookshelf, on the shelf with the alcohol we were looking at. And it is slightly smaller than the number of rabbits that we saw later on this evening. So let's assume that the number of these rabbits was 105. So, however, as you might have seen, we were not able to estimate actually the number of elements in the two sets. This is because of the size and distance effect that we are talking about later. So this actually leads us to the following conclusion, that there is something inherently vague to the numerical expressions. This is surprising because when we think natural numbers, we think about expressions that actually have exact references. And hence, in some contexts, even numerals have vague interpretations, actually. So this is the case, for example, in expression like there are 100 people in the room or 2,000 people participated in the demonstrations, in which case the actual intention of the speaker is actually not to approximate, number of people and not to give it the exact number, yeah? So, this is actually the phenomenon of so-called round numbers, which has been studied from various perspectives, mostly in pragmatics. And we will come back to it in our further investigation, because we actually assume that it could be that ANS-related system of representations is kind of a naturalized semantics for round numbers. But in this talk, we will actually stop here, looking at symbolic representations of numbers. And in this talk, we will actually look at the consequence of observation that an inherent feature of the ANS is the approximate or vague representations that the exact discrete input activates, actually. So in consequence, we formulate a term, vague input, that will allow us to speak about non-symbolic perceptual input and not to be constrained to symbolic representations only. And when it comes to a vague term, we understand it as a term that has a borderline cases of interpretation. So, for instance, when we say that the term red is vague, that means that there are some cases of redness that are difficult for humans to classify as red. So, in other words, the semantics of the vague terms is characterized by the existence of so-called borderline cases. So, in consequence, we may say that a vague input will be actually such an input that has also a borderline cases of interpretation. So, as I said on the beginning, our central endeavor is actually to define a conceptual space that models a structure of representations related to the approximate number system. And because of the analog nature of ANS, its representations can be actually considered as a certain type of analog representations of magnitude. So, in order to properly model ANS representational structure in conceptual space framework, we have to bear in mind several characteristics of analog magnitude representations. And there are 4 characteristics of the system. First one is that the system of analog magnitude representations is activated by discrete quantitative input. Second one is that it is magnitude sensitive. So this means that the bigger the quantity of the input, the bigger the magnitude represented in the system. Third characteristic is that the boundaries between the representations of the system are not actually sharp. So it is not clear whether the 39, for example, belongs to the scope of 45 or the scope stops for, let's say, 40, for example. So in other words, the vague nature of ANS entails the possibility of confusion between 2 neighboring numerical representations. And finally, the last characteristic of ANS of analog magnitude representation system is that its representations obey the size and distance effect. Okay, so it is important to note that our aim is actually not to conduct a study of analog magnitude representational system in conceptual space structure. Instead, we want to study a particular type of AMR. It is ANS-related representations of quantities. So you may say that our endeavor is quite modest, actually. There are multiple aspects, general aspects of such system that we actually shall ignore in the proposed model, and instead we focus on ANS-related representations that are activated in response to a constant visual input consisting of various sets composed of different quantities of identical blue dots, evenly distributed on a whiteboard. So it is only about this. And this input would look something like this. Okay? So even if the long term of our objective of our research actually is to understand representations of any set of discrete elements, and constructing a semantics for exact numerals, in this talk we actually will model the non-conceptual content of ANS-related representations. And in fact, exact numerals and sensory quantitative discrete inputs are claimed to activate the same system of representations. So by proposing a stretch of a model for a simple sensory input seems to be a quite natural step to take. Okay, so the next step is constructing the model, and in the construction of the model we use actually the idea that ANS-related representations are best characterized by spatial dimensions. So it seems obvious that the natural tool for modeling the representational structure of this system is actually a geometric model of representation proposed by Peter. So it's conceptual spaces, I mean. Okay, so one simple way of thinking about this kind of representation is proposed by Curry and Sarnecka, and it can be presented in the following way, actually. So as you may see, the line length is actually a direct analog of the number of objects, actually. So this means that the representations gets bigger when the increasement of the with the increasement of the input, actually. So as I mentioned before, the ANS represents the numerosity of a set by the extension of a space. So this also corresponds with so-called snark effect, and this stands for a spatial numerical association of response codes. And in short, the snark effect actually entails faster left side response to small numbers and faster right side responds to large numbers, for example, when we are classifying them parallel or by magnitude. And this association between numbers and space has actually been shown to affect cognitive process in a wide range of tasks. I don't want to go to details right now, but what is important in here is that this NARC effect actually shows us that our number comprehension reflects our experience, that every increment in numerosity is also an increment in spatial extent, and of course vice versa for decreasement. So in fact, ANS-related system of representation is strongly affected with this spatial correlation. Okay, so the next important step in the context of the model construction is the issue of prototypical representations in ANS. So we are actually argue that the certain types of distribution of dots on the board are cognitively privileged. This provides an opportunity to incorporate a prototype theory for model of ANS-related representation in the conceptual spaces. Simply speaking, some arrangement of blue dots on a board may be considered as a prototypical or a salience instance of a given cardinality than others. Okay, so to begin with, let us consider a two-dimensional conceptual space with height and length as quality dimensions, in which we consider a spatial arrangements of identical blue dots evenly distributed on a whiteboard. For the moment, we assume that dots can be actually organized in different shapes, spatially ordered or randomly distributed. Later, for the sake of the model simplification, we will actually consider only these shapes which are representable in the Cartesian coordinate system. So, as I said before, we offer the hypothesis that some of these arrangements will be more easily recognized by the subject as corresponding to the given numeral. And this situation we want to describe is actually following. So the subjects look at the different quantities of identical dots. Dots can be arranged in different ways. This figure actually contains only 4 dots, but it can be actually easily generalized to the greater quantities. And in a model construction, we actually consider only spatially ordered shapes, just for the simplicity. Okay, so these inputs would actually look like this. Okay, so in a similar way, we can actually distinguish the extended, continuous, and approximate representations of INS in terms of space occupied by their shapes. So the shapes of these representations correspond with arrangements of dots provided as a visual input in an estimation task. And if each of these possible arrangements can be actually straightforwardly represented in a conceptual space as ANS-related representation for 4. So, as in the case of colors, it seems pretty plausible that humans actually converge to some unified set of prototypes. So, we propose that in our model, the role of the prototype is played by dots which are the most evenly distributed. Of course, an empirical study has to be conducted to psychologically ground this assumption. But to support our hypothesis that evenly distributed dots are more salient instance of the distribution of dots, we can refer to the Tversky studies provided in features of similarity. This is well known, actually. So, according to Tversky, figures that are good in form, like he says, are perceived as a more salient or more prototypical type of figures. So, the left one will be more salient than the right one, actually. So, this distribution of dots will be more prototypical, or the shapes that occupies this, these dots will be more prototypical than this one. Okay, so for the sake of model construction, we propose to order the rest of the configuration of 4 elements, four element set of dots mentioned above, following to the degree of similarity to prototype. So the prototype would be the figure marked on the screen as A, actually. Okay. So the location of the other elements of a set is then determined by the degree of similarity to the prototype with regard to the one of the dimensions. So it's height and length, actually. In the similar way, we can actually model the sets of ANS-related representations of other magnitudes, and we actually suspect that models for bigger numbers will differ from this presented on the screen, because these representations take into their scope actually also a neighboring candidate. So, for example, some inputs that activate, let's say, the representation of, for example, 17 will be also activated by some non-prototypical representations of 16 and 19, maybe. We have to conduct some research to actually look how it will be. So the application of Voronoi tessellation to the conceptual space model allows us to map the entire conceptual representative structure of size provided by the ANS. So these points will be actually the prototype, and we finish with this kind of a tessellation. The problem with this tessellation is that it is not vague, actually, as we may see. So the borders between the neighboring representations of concepts are not vague, and to achieve this, we can actually use this proposal of Duven and others to the use of the prototype groups. So this is actually this proposal, and as claimed by Duven, in the case of vague terms, it can happen that it is more adequate to consider a set of cluster of prototypes instead of a set of points. So in other words, the meaning of some terms is more adequately modeled when we consider the division of the corresponding conceptual space as generated by groups of points corresponding to the prototypical representation of meaning. So in short, this model requires treating cases of object neighboring to the prototype as the prototypical cases and using them as generators of subsequent tessellations. So as a result, we will finish with something like this, actually. It's actually, it's a simplification also, but it would look something like this. So we suspect that for the larger numbers, regions of tessellation will differ from the picture above. It is because regions representing larger numerical values are not only contiguous upon the regions representing two closest values in the numerical progression, but also are contiguous upon other proximate regions. So we may say that region A is contiguous upon if the ratio of numerical values represented by both regions is close as possible to 1:1. Of course, the exact value of the ratio should be actually ascertained experimentally, but for the purpose of this model, we can actually venture to say that the deviations should not exceed 0.1, but this is actually a priori, so we have to check it. And this rule actually explains why the region representing 5 in conceptual space is contiguous only upon regions denoting 4 and 6, while the regions representing, for instance, 33 is contiguous upon 6 regions. So it would be 30, 31, 32, 34, 36, because the amount of ratio is different. Okay, to sum this up, we wanted to propose a treatment of representation of quantity that actually embraces pre-verbal numerical concept, in particular the representations related to the approximate number system in conceptual spaces. It is important to note that the proposed model of ANS-related representations is easily and intuitively reconciled with the size and distance effect, and both effects actually show that the similarity between ANS-related representations in conceptual space are designed by this similarity is designated by the inverse ratio of the magnitudes being compared with each other. So in other words, the smaller the ratio between the magnitudes, the more similar objects are. So finally, the ANS model is magnitude sensitive, as it's supposed to be, and it implements actually the vague characteristic of analog magnitude representations. Okay, so now what we have not done, in the presented model, we actually not take into account the fact that the blurred borders can cover more than just one neighboring quantity. So when you look at the models of ANS, you can see that 10 might be actually confused with it's this linear progression. 10 might be actually confused with 12, 13, 11, because they are actually in the scope of one representation. So the model that we propose shall be modified in a way to account this feature actually of ANS. And in the presented model, we have also not taken into account the issue of the conceptual change from core processing with ANS towards the exact understanding of numerals. And we actually use the idea that ANS-related representations form a linear progression. But according to some of the cognitive scientists, ANS-related representations actually do not form a number line. So correlation with other conceptual inputs are necessary for accounting this progression. Okay, at view end we can refer to the story of Alice again, which seems to be a nice illustration of relationship between approximate number system and parallel individuation system, and a quite nice summary of our presentation. And it goes like this, and I leave you with that, and that's end our talk. Thank you.